All right, let's dive right into this explainer and explore a total paradigm shift in how we think about, analyze, and report on complex human systems. If you're used to traditional quantitative research, you know the feeling. It sometimes feels like your data is forcing you into this really rigid box. Well, today we are breaking out of that box by exploring fuzzy set qualitative comparative analysis, or fsQCA. This isn't just a new statistical tool, it is a completely different way of seeing the world. Because let's face it, human behavior isn't some neat little math equation. It's messy, it's intertwined, and it rarely happens in isolation. fsQCA actually embraces that messiness to help us uncover how things really work. So here's our roadmap for the explainer today. We're going to hit 5 key stops: escaping the linear matrix, set theory and Boolean logic, conditions, outcomes, and recipes, the PhD writing shift, and finally, mastering configurational causality. Let's get right to it. Section 1. Escaping the linear matrix. Time to move beyond basic regression. We have to start by calling out the fundamental limitations of traditional regression analysis and its strict reliance on symmetrical linear relationships. I mean, think about it. Does a normal distribution truly capture the crazy complexity of the social sciences? Or could there be multiple, totally different paths that lead to the exact same outcome? Regression inherently suggests a linear relationship between input and output. Say we're trying to figure out what makes a high-performing employee. A linear model assumes a neat, straight line, like more training automatically equals more performance. Even when these models try to account for nonlinear relationships, they still rely on rigid statistical assumptions. But human systems just don't act like a straight line. Variables don't act independently. They tangle together in complicated, intertwined ways. As Fisk pointed out back in 2010, cases are best understood as configurations. What does that actually mean for us? Well, in this framework, an employee isn't just an isolated age variable or a solitary salary dot on a scatter plot. Instead, fsQCA looks at them holistically, as a unique combination of set memberships. You are looking at a specific type of person, defined by a unique combination of attributes. Maybe they belong to the set of highly experienced and the set of remote workers. It's a massive shift from studying isolated variables to studying holistic configurations.
Moving on to Section 2, Set Theory and Boolean Logic. This is the absolute foundation of fsQCA.
Now that we've broken out of the linear matrix, we need to understand the underlying code governing these complex configurations. This brings us to system theory, fuzzy logic, and Boolean algebra. First up is equifinality. I love this concept. Think of it like baking a cake. You could use a vegan recipe, a gluten-free recipe, or a super traditional butter-heavy recipe. Completely different lists of ingredients, right? But the outcome is still a delicious cake. In standard regression, we usually search for the one best model to explain an outcome, but your data has multiple recipes for success too. fsQCA embraces the fact that there isn't just one single way to achieve a result. Multiple, entirely different combinations of conditions can get you to the exact same destination. Next is causal asymmetry. The big takeaway here is that just because a cause is sufficient for an outcome, it doesn't automatically mean the inverse is also true. In traditional correlational methods, if X goes up and Y goes up, we just assume if X goes down, Y goes down. That's symmetry. Causal asymmetry throws that right out the window. Going back to our workplace example, the conditions that lead to high employee performance might be completely different from the conditions that lead to low performance. This is crucial. If a company only studies why people succeed and naturally assumes the exact opposite is what prevents failure, they are operating on completely flawed logic. The presence of a factor might cause an outcome, but taking it away doesn't automatically reverse it. Then we've got conjunctural causation. This means ingredients rarely act on their own, they have to interact conjuncturally to produce a result. We're talking about set intersections here, the logical and. Let's continue with our employee. Maybe having a highly supportive manager, let's call that condition A, does absolutely nothing for productivity by itself. But a supportive manager and flexible working hours, condition B, suddenly those two intersect to create a powerful catalyst for high performance. We're looking at how these memberships intersect to create a pathway that is actually sufficient for our outcome.
All right, Section 3, Conditions, Outcomes, and Recipes. Let's get our vocabulary straight.
Let's see how all of this builds our practical vocabulary for actually executing an fsQCA study. If you're taking notes, definitely grab a screenshot of this translation guide because swapping these terms is absolutely essential. We are completely dropping independent variable in favor of causal condition. Why? Because as we just saw with conjunctural causation, nothing acts independently. we drop dependent variable for outcome. And instead of talking about messy, hard-to-interpret interaction effects, we talk about causal recipes or pathways. It's a really simple swap, but it immediately reframes your mindset from measuring isolated impacts to evaluating combined sufficiency.
So how do we actually do this? This sequence reduces thousands of potential configurations down to the minimized, actionable causal recipes. This is the mathematical engine room of fsQCA. Let's break it down simply. First, the software builds a truth table. If you have k causal conditions, say you have 3 conditions you're testing, the table generates 2 to the power of 3, or 8 possible logical combinations. 4 conditions, that's 16 combinations. Next, we test for sufficiency by looking at the raw consistency of each row. Finally, we apply the Quine-McCliskey algorithm. Don't worry, you don't need to do the math by hand. Just know this algorithm is essentially a fancy mathematical filter. It strips away the noise and deletes conditions that don't actually influence the outcome, leaving you with just the essential, minimized causal recipes.
Which brings us to section 4, the PhD writing shift. It's time to talk about configurational language. Getting the math right is really only half the battle. Now we have to radically shift how you actually write and defend your findings. There is a massive trap a lot of researchers fall into here. You must completely eliminate that old net effects, variable-oriented language on the left and fully embrace the sufficiency language on the right. If you run a beautiful, sophisticated fsQCA analysis but write in your paper, variable X had a positive impact on Y, your reviewers will tear it apart. You aren't testing for net effects anymore. Your writing must accurately reflect Boolean logic. You need to confidently state things like, a high degree of membership in condition X combined with a high degree of membership in condition Y is sufficient to produce the outcome. And when you inevitably face pushback, and trust me, you will face pushback from committee members deeply entrenched in regression mindsets, this quote is your ultimate shield. You are not measuring independent influence, you're measuring complex combinations. Point them directly to this literature. Your methodology isn't just a different math formula applied to the same old ideas. It is a fundamental theoretical choice to prioritize combinatorial complexity over isolated net effects. You really have to stand firm in this new paradigm. Finally, section 5, mastering configurational causality. Let's talk about validating those recipes. Let's distill the best practices to make sure your configurational analysis is rigorous and empirically sound. These are your structural guardrails. Let's define the jargon in plain English first. Think of consistency as reliability. Does this specific recipe almost always work to produce the outcome? You generally want this score above 0.8. Think of coverage as popularity. Of all the cases that achieved the outcome, how many actually used this specific recipe? That should exceed 0.2. Maintaining these thresholds proves your recipes are mathematically valid. Also, remember causal asymmetry from earlier? Because of that, you must run your analysis twice, once for the presence of the outcome and once for its exact opposite, its complement. And of course, you'll use those truth tables to spot and resolve any logical contradictions in your data. So, as you step back into your own data, remember that the world is incredibly complex, and it's about time our methodology reflected that beautifully tangled reality. We've moved past linear assumptions, we've embraced fuzzy set memberships, we've learned the language of causal sufficiency, and we've set the rigorous thresholds needed to defend the work. Those hidden recipes are waiting in your data right now. The only question is, what will you uncover first? Thanks so much for joining me on this explainer, and happy analyzing!